Hello, everybody. So today we're going to be talking about the mathematical structures which underlie classical mechanics, which namely will be symplectic geometry. So as an outline, we're going to start with just the Euler-Lagrange equations and Hamilton's equations as they're typically presented in a physics context. Then I'm going to present Hamilton's equations in particular in sort of a more symmetric way, but still something that you might see in the context of physics. But then I'm going to talk about those geometric spaces which are underlying classical mechanics, namely configuration space in the Lagrangian setting and phase space in the Hamiltonian setting. I'll then relate these to differentiable manifolds and then talk about how these configuration spaces and phase spaces may be viewed as manifolds which are associated to essentially the physical space. So in the context of configuration space, this will be realized as the tangent bundle. And in the context of phase space, this will be realized as the cotangent bundle. Then specializing to the cotangent, to the phase space discussion specifically, I'll talk about the relevance of symplectic geometry to encoding the structure of classical mechanics here, as well as the specific physical data involved here, which is the Hamiltonian function, and then as well as the Hamiltonian vector field. So we'll then present Hamiltonian mechanics in a global geometric way, and then we'll finish by showing locally how to recover Hamilton's equations in the sense which you would have seen in a physics class. Okay, so just as a recap, we'll start with the Euler-Lagrange equations. So recall that these take the following form, where the qi's are going to be our generalized coordinates. So you get one equation for each index I. And we have this special function called the Lagrangian, which is a function of these generalized coordinates qi, as well as the velocities, which are the qi dots. Right? And then the Euler-Lagrange equations are going to be second-order differential equations given in terms of these two types of quantities. Conversely, Hamilton's equations are going to be first-order. They're going to look like this. And instead of the Lagrangian function, we have the Hamiltonian function. And this one is going to be a function of the generalized coordinates, as was the case with the Lagrangian. But instead of the velocities, it's going to be a function of the generalized momenta, which are pi's. So the generalized momenta, pi, will be equal to the partial derivative of the Lagrangian with regards to the generalized velocity. Right? So in particular, in order to know the pi's, you need to know the Lagrangian, even when you're dealing with this stuff in the Hamiltonian formalism of mechanics. Right? So in terms of the actual dynamics, right, we have Hamilton's principle. So this is saying that the physical trajectories should correspond to the extrema of the action, and the action is going to be the integral of our Lagrangian with respect to time. Right, so you go through this whole variation procedure, considering other paths which would be consistent with the constraints on the problem, and then you essentially find the extrema within this class of paths, and then that will give you q as a function of t, the qi's as a function of t, which are your trajectories. Right, so you could treat both the Lagrangian and the Hamiltonian formalism from such a variational principle, if you like. But this is the fundamental physical statement, which is resulting in the Euler-Lagrange or Hamilton equations. Right. So the Hamilton's equations in particular, they treat the generalized coordinates and the generalized momenta fairly similarly if you look at the structure of the equations, except for this minus sign which is coming off, which is sort of throwing off the symmetry. But just via some algebraic manipulations, really more of just an inference, you could recast Hamilton's equations in a more symmetric way if we write them like this. So we can write them in sort of the notation of a column vector. We'll call it eta. You can write it like this, as long as we make eta written in terms of the generalized coordinates and the momenta as such. So this is going to be, if we have n generalized coordinates, this is going to be a 2n dimensional column vector, right? And then our omega should be a matrix which takes the following form. So this is going to be a 2n by 2n matrix. We're going to get zeros for n by n parts in the upper left quadrant, as well as the lower right quadrant, and n by n identity matrices in the other quadrants, with one of them coming in with a minus sign. So just looking component by component, this is just going to reproduce Hamilton's equations, which we presented earlier. Okay. So in terms of Lagrangian mechanics, the space which is relevant for us is what's called configuration space. And we can think about the coordinates on the space being the generalized coordinates, so the qi's, as well as the generalized velocities, the qi dots. So these are not just numbers or functions here, these are locally characterizing a geometric space. So this is a configuration space for these particular coordinates, right? So I would also like to mention that the generalized coordinates themselves, just ignoring the velocities, will also constitute a space. And this is being done locally in this case, but it will actually have a more global nature. Right. So the point is that in terms of the mathematics, both of these spaces, so configuration space, which has both the coordinates and the velocities, or the generalized coordinates and the velocities locally labeling them, as well as the space of just the generalized coordinates, are going to constitute examples of differentiable manifolds, right? But in particular, we're not using the structure of a metric in this case. We're just having the differential structure so far. So phase space is somewhat similar. So here the coordinates are going to be the generalized positions and the generalized momenta, as opposed to the generalized velocities. So these are locally characterizing this space, phase space. This will also constitute a differential manifold, and as before, we also get a differential manifold associated with just the coordinates. So one thing I would like to mention about both configuration space and phase space is that if our space of the coordinates is n-dimensional, both of these spaces are going to be 2n-dimensional. Right. So in terms of the precise structure which is going on here, phase space will be realized as what's called the cotangent bundle. So this is what's relevant in Hamiltonian mechanics. And configuration space will be realized as what's called the tangent bundle over our differentiable manifold. And this is what's relevant in the Lagrangian case. Right. So the tangent bundle, the notation for this, basically is built out of the data for any differentiable manifold. So for any differentiable manifold, we have a notion of a tangent bundle. And what we do to get this is we take these vector spaces, which are associated with each point on our differentiable manifold, and we glue these together basically in a smooth way to construct our tangent bundle. Right. So a little bit more precisely, without going into the full details here, we're going to have our 2n-dimensional manifold, which is the tangent bundle. Our space, which is locally just characterized by the generalized coordinates, will be m. That's going to be n-dimensional. And these are going to be related by a smooth surjective map. So this is like some kind of a projection appearing right here. Okay. So phase space is going to be similar. This is what comes up in the context of Hamiltonian mechanics. This again is going to be a 2n-dimensional space. This is built out of the dual vector space at each point for our differentiable manifold, as opposed to just the vector space. And we're similarly going to get a projection from the cotangent bundle to our manifold M. Right. So in terms of that symmetric presentation of Hamiltonian mechanics, which I wrote down earlier, we had this matrix omega which came up, right? And this actually is going to turn out to just be a local realization of what's called a differential two-form. And this one in particular is going to essentially carry the structure of classical mechanics. This is what's going to be called the symplectic form. Right? So this is what this is realized as in a local expression of the thing in a particular choice of coordinates. But generally speaking, a symplectic form is going to be a closed 2 form, which is non-degenerate, right? So closed is referring to the exterior derivative. This acts on differential forms. This is saying that the exterior derivative of this 2 form should be 0, and this thing should also be non-degenerate, and that's going to be our symplectic form. And we realize it locally in a particular choice of coordinates as omega. Right. So what were the choice of coordinates in which we could realize this symplectic form with these components for the matrix? This is what's called Darboux coordinates. So Darboux's theorem says that for any symplectic manifold, about any point we can find these Darboux coordinates such that the symplectic form takes this nice form in terms of its components. Right. So this will, in that case, precisely reproduce the matrix omega, which was introduced earlier in the sort of local version of Hamilton's equations. Okay, so now we want to present Hamiltonian mechanics in a more geometric way. Everything which we would have done before would have been local, and actually, moreover, would have been done in Darboux coordinates, which only via these mathematical results do we know actually even exist, right? So, but the point is that the symplectic form afforded us the general background for classical mechanics, but in order to talk about dynamics of any particular problem, we also need the data of a Hamiltonian function. And then associated to this, we're going to get a special vector field. Right. So the Hamiltonian is going to be realized as a function of the cotangent bundle. This is just since the Hamiltonian was a function of the generalized coordinates and the generalized momenta, that's where this is going to be. So it's going to be a function of the cotangent bundle, which has these as local coordinates, right? So we're going to say given some Hamiltonian function h like so a function on the cotangent bundle, a Hamiltonian vector field is going to satisfy the following global equation related to the symplectic form and the Hamiltonian function. So this is saying that essentially the contraction of our Hamiltonian vector field into the symplectic form should be equal to the derivative of the Hamiltonian function. Right? And this is exploiting the fact that omega is non-degenerate in asserting that such a vector field actually even exists. Right? But this is a global equation which is going to hold throughout our cotangent bundle. So these are differential forms defined on the cotangent bundle. Right. Okay. So now we want to think about what the physical trajectory should correspond to. And in terms of the differential geometry, this is actually characterized in terms of the Hamiltonian vector field. So the assertion is, in this case, that physical trajectories will correspond to what are called integral curves of the vector field x of h. So this vector field was completely determined by the symplectic structure as well as the Hamiltonian. And then essentially the dynamics are just given in terms of this natural concept, integral curves associated to this vector field. So how do we actually recover Hamilton's equations in local Darboux coordinates in practice? So starting from that general expression relating the contraction of the Hamiltonian vector field into the symplectic form and tying that into the derivative of the Hamiltonian function, if we take that thing and write it locally in terms of Darboux coordinates, that entire expression which is valid globally, then we can find an expression for the components of the Hamiltonian vector field in these coordinates as such. So these are given via that global equation in terms of derivatives of the Hamiltonian function appearing as prefactors to the basis elements of this tangent space. Right? So then if the essentially integral curves of this vector field are going to correspond to our physical trajectories, then that's suggesting that since the components of these integral curves are going to be pi dot dpi plus qi dot dqi, so that defines the integral curve, we just equate the coefficient prefactors in front of those basis vector fields, and then we recover in these coordinates precisely Hamilton's equations, as would be typically presented in a physics class. So from this global perspective, we've recovered exactly what Hamilton's equations should look like locally in the context in which we're familiar. Okay. And symplectic geometry is a very interesting field. This is what's going to be relevant in classical mechanics, and it's most easily seen through the Hamiltonian formalism, which is a major motivation for considering this formalism in the first place in a physics class. Okay. Thank you, and I hope to do more videos on symplectic geometry soon.